All right. Hi there. My name is Jackson Church. I also happen to be Miss Gambley's son, but I'm studying physics at university in Brisbane. And some of you might remember me from when I came and did some science shows for you all a couple of times over the past few years. But I'm here today to answer some of your questions about light, electricity, and energy. And Mrs. Churchill sent me these questions so that I can answer some of them for you. And there are some pretty fantastic questions. So let's get to it. So the first question is, why is only some light visible? And let me tell you, this is a big question, and it's got a lot, it covers a lot of areas. So I'm going to do my best to condense it down. So starting with the beginning, light is also known as something called the electromagnetic spectrum. And I have a little picture here to show you, which will help hopefully. So here we are. This is the electromagnetic spectrum, this big blue bar in the middle. So as you can see, it's got all the different types of light on it. It's got gamma rays, X-rays, ultraviolet, all the way down through infrared, microwaves, all the way up to radio. And radio can, there are types of radio waves like TV waves or even some Wi-Fi. That's all types of radio waves. So these are all actually types of light. And as you can see down the bottom, we have this rainbow, and this is the visible part of the spectrum. But this rainbow, it actually all fits right in this little sliver right here. So it's a massive spectrum, and we can only see a tiny little part of it. But fortunately, we have developed some tools and some machines to help us see other types of light, like X-rays. For X-rays, we have X-ray machines, and stuff like infrared. We can see infrared light with night vision goggles. And so to understand why we can only see this amount of light, we actually have to look at the eye. Now, our eye has a few special types of cells that detect light, and these are called cone cells. And we have three types of cone cells: red ones, green ones, and blue ones. And these detect when you see red, green, or blue light, or a mix of the three. Now, this is important because these three types of cones in our eye let us see this whole spectrum, this rainbow. But we can't see the rest of this spectrum because we don't have the right cones to see the rest of the spectrum. But funnily enough, there are some animals that can see the rest of some other parts of the spectrum, like, for instance, butterflies and some birds. Some butterflies and birds have a type of ultraviolet cone in their eye, which lets them see ultraviolet light. And if you're interested in seeing what they can see with their extra cone, they can see a little bit more color than we can. I've got some pictures here of some flowers that look that sort of look like what it would look to a bird or a bee or a butterfly or something. And so this is what it looks like to us, this nice yellow flower. But over on the right here, this is what it looks like under UV light. So this is what it would look a bit like this to a bird and a butterfly. And you can see it looks very different to the way we see it. And I've got another couple of pictures. This one's very striking. You can see that red from, we only see the yellow, but in ultraviolet you can see red and, a little bit of purple down here. There are a whole bunch of other colors that we just can't see. And I believe there's also, this one's my favorite. So we have this really bright yellow flower over here, and it's got this very clear ring in ultraviolet, which is pretty cool. But that's the main reason that we can't see the rest of the electromagnetic spectrum, is because our eyes don't have the types of cells that pick up these types of light. We can only see this part of it. So there are many other types of light that we can't see, but we can see it using other types of tools. So that's a fantastic question. So the second question is light actually hot? And as I was saying before, there's a full spectrum of light, which covers a lot of areas other than just what we see. and heat is actually one of them. So when a light wave hits something, some of its energy is actually absorbed by the object, and the energy causes that thing to heat up just a little bit, just a tiny bit. Now it turns out that that whole spectrum, all of those different types of light actually have different sizes, and this just means that the light wave might be really long, it might be spaced out, or the light wave might be really, really tiny, it might be short and sort of more compact. But when you shine a light on something, it actually depends how big that thing is as to whether the light is absorbed or not. So when we have a light wave coming onto something small, it'll only absorb small rays. Big ones will just pass straight through it. And likely if we have a big object, it won't really absorb the little light, the little short light waves. It'll only absorb the big ones. So you could take X-rays, for instance. When we think of X-rays, we think of X-ray machines, and how they work is sending X-rays across our skin. Now, X-rays are tiny, tiny, tiny things. They're microscopic little wavelengths, and our skin and muscles and things are too big to absorb that light. However, so it passes through. However, our bone structure is just the right size to absorb some of that light, and so that's how we see our bones in an X-ray. Our bones absorb the light of X-ray light, but our skin and muscles just let it pass straight through. And in the case of our bodies, our skin and our bodies are just the right size to absorb infrared light. So infrared light is the type of light that we sort of we see as heat, because it's the right size for us to absorb. Now, when you go out and stand in the sun, you can feel all of that light and all of that heat hitting your skin. And that's like the sun puts out a lot of light, and a lot of it happens to be infrared. And so that's how we feel heat. It's the light coming down from the sun or from a fire or anything that puts out infrared light. We can feel that light because it comes in and our skin absorbs that, and that heats it up just a little bit. It just gives it that little bit of energy, which it absorbs as heat. Now, the last question on light is, how is light created? And the actual process that creates light is quite complicated, but I'll try and give you a quick explanation. So light particles are called photons, and photons come pouring out. They come streaming out of any light source, like the sun or lights in a house or a torch or something like that. But photons are created all the way down at the atomic level, at the atomic scale, so really, really, really tiny. And how they come about is when an atom gets a little bump or a little hit from another atom, sometimes it can release a photon, which is a little bit of light, and then this photon leaves, and it goes and shines on something. It's like a little bit of like a little laser. It goes and shines on something. And when you get a lot of atoms sort of bumping into one another, they keep shooting off all these photons in all different directions, and that's how you get light from, or that's how light's created. Sometimes it'll shine on a wall or a floor or some kind of object, and sometimes it'll even end up in your eye, where your eye will detect it using those cones I just talked about. And you won't be able to see the photon itself. It's way, way too small, but you'll be able to see the color that it shows you and the effect that it has on your eye. Now, when you turn on a light, what's actually happening is you're getting a little bit of electricity to go through the light bulb. And what it's doing is the electricity causes all the atoms to sort of jiggle around and bump into one another. And they keep sending off photons, lots and lots of photons. And that's what happens in a light bulb. You send the electricity through, the atoms jiggle around, and they give off lots of photons, which gives off lots of light. And so the simple explanation, I suppose, to where light comes from is light comes from atoms exchanging energy when they bump into one another, and they give off photons. Now, the real explanation of where they come from is to do with electrons down at the atomic level, which I'll show you in a minute, but that's basically a pretty good way of thinking about it. So for the next question, we're going to move into electricity. So the question is, what is static electricity? And most of you should have heard this before, if not felt it. You can often feel it when you touch something like a doorknob after rubbing your feet on the carpet, or sometimes after you've been in the car for a long time. If you touch the outside of the car, it might give you a little shock. This is what static electricity is, but it's also the reason for why your hair stands on end when after jumping on the trampoline for a while, or if you rub a balloon in your hair, something like that. That's all static electricity. So the way static electricity works is it comes from atoms. So when we look at an atom like this, this is a reasonably good model of an atom. We'll notice that it has three types of what we call subatomic particles. It's got things called electrons, protons, and neutrons. Now, electricity works off electrons, so we don't really need to worry about these other two at the moment. We can just look at these blue electrons. So electricity is what happens when these electrons jump from this atom to another atom. And I've got a little animation here that can show you this. You can see all of these electrons here jumping across to each of the atoms, and if you follow one of them, you'll see it jumping across to the neighboring atom. And what happens is when you have lots of them, like in this case, you can see them all, they all sort of flow along, and we can think of this as something like an electric wire where the electricity is flowing along through it. And that's what these electrons are. They are the electricity. Now, static electricity is where these electrons start piling up somewhere. So when those electrons start piling up in a certain place, they sort of start pushing against each other and they start jostling because they don't like to be next to each other. And so they start sort of building up a pressure almost. And when you come along and touch the car, for instance, if it's statically charged by all those electrons, if you've got lots and lots of electrons, if you come and touch it, then they suddenly go, oh, there's a place that we can go that's not here. And so a lot of them will escape into your finger. And that's what that little spark is, that little shock. It just it shocks you a little bit. That's all of the electrons jumping across into your finger. And that's what static electricity is. It's just a build-up of electrons which you can touch, and it'll they'll all just jump across into you. But don't worry about the shock that it gives you. It's not very dangerous. It's only a tiny amount of electricity. It's completely harmless. So continuing on with electricity, the next question is electricity everywhere? Is it even in space? So thinking about what we've just learned about how electricity is just electrons jumping across between atoms, and you sort of get a flow of electrons, and that's what we call electricity. So down here on Earth, at least, there's electricity everywhere because there are electrons everywhere. All matter is made up of atoms, and all atoms have electrons in them. So you could sort of say there's electricity everywhere. But what's really happening is some electrons might be hopping over to a neighboring atom and then back again, or over a couple of times, but they're not really going anywhere. And so you wouldn't really call it electricity. There's a lot of charge, which is another word that you could say electrons have. They sort of move around a little bit, but not really. You wouldn't call that electricity. So there's kind of electricity everywhere in a sense, but it's you wouldn't call it electricity unless it was in a wire that we've connected to a generator or something. So out in space, however, I know they use electricity on the space station. They use it to run all their computers and lights and experiments and stuff, just like we do here down on Earth. But out in deep space, out where there isn't any air, there's no planets or meteors or comets or anything really. Do you think electrons would be flowing? Not really, because there aren't any atoms out there. If there's no atoms, then there can't be any electrons. So electricity can't really exist out in deep space because there's nothing for it to flow through. So that's the simple question is there isn't electricity in space, but there are electrons. On Earth, at least, there are electrons everywhere. So you could almost say there's electricity all around us, but it doesn't really do anything until we harness it and put it in wires and devices and things like that and get it to run stuff. Another really cool topic that you could look into is something called conductors and insulators. I'm not going to touch on this for too long though, because you'll probably learn about them in class. I hope it's a great topic, but they're a whole different topic on their own. But yeah, conductors and insulators, they're very interesting to learn about how electrons flow between different types of atoms and how we generate electricity with those electrons. So moving on to energy, and the next question is, what objects have energy in them? So there are lots of types of energy. There's chemical energy, there's electrical energy, movement energy, which we call kinetic energy, and a few others. But there's another type of energy called heat energy, which everything has really. So when you boil a kettle at home, you're adding heat energy to the water, you're heating it up. And you're giving the water more heat energy. Now, if you cool that water down, you're removing that heat energy. And you can imagine cooling that water all the way down so that it becomes ice. You're removing a lot of that heat energy, but it hasn't lost all of its heat energy. You can still cool it down more. It just becomes a colder block of ice. And it turns out you can keep removing that and keep making it colder and colder and colder and colder. But you can't do it forever, however. We do have a limit to how much heat energy you can get out of it. And when you remove all the heat energy out of it, so it has no heat energy left, it gets to a temperature that we call absolute zero. And this is sort of the limit. This is about how cold anything can go in the universe. And it's negative 273 degrees. So it's very, very, very cold. And when things get that cold, all of them have no heat energy. So you might say, well, it has no more energy left. If it's not moving and it has no electrical energy, it now has no heat energy, it might have no energy. But there's one more type of energy, and that's called rest energy. Now this part can get a little bit weird, because atoms and matter itself, physical objects, actually have energy inside them. I mean, it's quite a lot. Now, normally I wouldn't show you the equation, but I feel like you've all seen this equation before. So, this equation here, E equals mc squared. This is Einstein's famous equation. And what this equation shows us is essentially energy is equivalent to mass. So E is energy, and M is mass, and C squared is just a constant here. So we don't really need to worry about that. All we need to look at is E is equal to M. And that means that energy is pretty much equivalent to mass. So mass and energy are sort of like the same thing. It means that we can turn atoms into pure energy, and back again, we can turn energy back into atoms. So the short answer, I suppose, to what objects have energy in them is that, well, every object has energy in them, every single one. I mean, if it didn't have any energy, it wouldn't exist, because energy is what sort of makes it exist in the first place. So every object has energy in it, yeah. Now, the last question you all asked was, if energy can't be created or destroyed, how did it get here in the first place? And this is a fantastic question. It gets asked every now and again. But I'll tell you a little secret. No one knows. No one knows where energy came from, energy and mass, because if energy can't be created or destroyed, we've got the same amount of energy in the universe at all times. And so what we have to do is take it all the way back to the Big Bang, the start of the universe. That's when all of the energy just sort of popped into existence. And I can tell you there are a lot of people trying to understand this moment in time, because it's very difficult to understand. All of our equations that we use in physics, they don't really work right at the start of the universe. All of the equations don't really describe what's happening there. And we're not sure what space was like at that moment. So yeah, where did energy come from? No one really knows. It just popped into existence at the Big Bang. And the Big Bang itself, no one really knows where it came from, or what was before the Big Bang, if anything was before the Big Bang. And it's an ongoing area of research in the world at the moment, because yeah, we just don't know what came before the Big Bang or anything. And it's probably one of the hardest problems we have at the moment in the world to try and understand, wrap our heads around. But that's sorry, I can't give you any more detail into that. I don't know myself, because not many people do know. All right, that's about the end of the questions. Yes, some of them were pretty complicated and big questions with some difficult answers, and a lot of this is actually only taught at university, so don't worry if you didn't understand some of what I said, but well done for thinking them up and asking the question, trying to understand. Good luck in going back to school if you are, and getting used to the way things were. And once again, thanks for the questions. They were fantastic. And don't stop thinking them up.